So today we're going to take a look at questions that involve not and or, and they're counting problems, of course, because that's this whole section of material, this whole chapter. The not questions are the challenging ones. The or questions are pretty easy if you just read them correctly. The computation for the or questions is easy, okay? The computation for the not questions is more difficult. So let me actually introduce you first to the complements principle of counting. Complements principle of counting says the following. The number of ways that an event can occur is the total number of ways that anything could happen, right? Anything can occur, minus the ways that whatever you're looking for can't happen. There's three equivalent formulas here, and they feel and look very much like the complements that we saw when we were looking at sets. Do you remember these formulas? They're exactly the same. When we're looking for the complement of a set and how many items are in that set, we do it the same way as what we're doing here. Now, I'll warn you in advance, the examples that we're going to do are all based on the same cards examples we were doing last time. I sometimes get flack because the homework is not just all cards, and I understand that. The principles are all the same. If you're focusing on the fact that it's cards, you're missing the point of what we're doing. Okay, so the application itself, like the context that we're working with, isn't the point. Okay, it's how we're doing the other pieces around it. So try and focus on the pieces that are coming into play and how they're structured, and then apply that when you're looking at different contexts in your homework. And as always, if you're having questions, I don't see how this one works with what we've done, send me an email. It will come straight to me. Chloe and I have been talking about some that she'd had some questions on. I'm more than happy to answer questions, okay? And the send your instructor one that you can do straight from inside of my math lab is fantastic because I can see the exact problem that you are working on because everybody has a different problem number 3 or whatever it is, right? So I can see the specific problem you are being given and can answer very clearly for that problem. So that's a very good tool. All right, so we're going to take a look at the way that these are asked. So generally speaking, they either give you or you're asked to find something that you already know how to find. So on this one, we're being told there are 2,598,965 card poker hands. We did that last time, okay? So that's not something that you haven't seen. And we want to know how many contain the following cards. Now, anytime this description is given, this part in parentheses may or may not be there. But whether it's there or not, this is how you should think about the question. Okay? This says at least one card that's not a club. So when you see that phrase, at least one, that's recognizing a not scenario. Right? So when you see at least one doing something, it means something is not happening. In particular, what cannot be happening in order to satisfy this condition? All right, there can't be anything, right? It says at least one card that's not a club, so I can't have all clubs, correct? I could have 4 clubs and that'd be fine, but I can't have all clubs. So this part that's in parentheses is helping to identify what you can't have. This is the complement of having all clubs, not cubs. Let's do clubs. So when you see at least one, make yourself a note. That's sort of like that red flag piece that says, I'm in the complement situation. So even if the part in parentheses isn't here, I need to be asking myself, what can I not have? What can I not have here happening? And this one is I can't have all clubs. So what does that mean I need to do? Well, it means I need to find out how many ways I get the number of ways I get all clubs. That's really what it means. Now, we talked through how to do that last time. I don't think we did it for clubs. I think we did it for diamonds, but it's the same process. How many clubs are there? 13. And if I had all clubs, it would mean I have 5 of them, right? All 5 of them. So this is 13C5. I have 13 factorial over 8 factorial and 5 factorial. Is that okay? Okay. So we're going to work this out just like last time. 13, 12, 11, 10, 9, and 8 factorial over 8 factorial, and then 5, 4, 3, 2, and 1. So the 8s are going to go away. What else can go away? Okay, the 5 and 2 make the 10, and 4 and 3 make 12. So I'm left with the 13, the 11, and the 9. So what would that value give me? 1,287. That's how many hands are all clubs. Okay, everything in the hand is clubs. So if there's 2,598,960 hands total and 1,287 of them are what we don't want to have, how do we figure out how we satisfy the conditions we do want? We subtract. And that's all the complements principle of counting says. It says that the number of ways that I get, in this case, at least one club is the number of ways I get anything. That's that 2 million number. At least one, I didn't write that right. At least one just going to shift it all around. At least one not a club, if I get my phrase right. That's what it wanted. Number of ways I get anything minus the number of ways I get all clubs. Okay, so the number of ways I get anything on this problem was given to us, or if it weren't, we could have found it. 2,598,960. The ways I get all clubs was the 1,287. And if I subtract, what do I have? Hands or ways or something like that. So when you see the phrase at least one, you need to ask yourself, what can't be happening to satisfy this condition? Because here's the reality. What you don't want to do is try to figure out, well, how many ways do I get 1 club? And how many ways do I get 2 clubs? And how many ways do I get 3 clubs? And how many ways do I get 4 clubs? And how many ways do I get 0 clubs? Because then I'd have to find 5 different pieces of information and add them all together. This way, I only have to find 1 piece of information and subtract. This is way easier. Okay? Let's try another one. This one says, cards of more than 1 suit. What cannot be happening? All 1 suit. I cannot have all, and I'm going to write them out just for the purposes of saying so. I cannot have all hearts, all clubs, all diamonds, or all spades. That's what I cannot have happening. Does that make sense? Well, I know how many ways there are that I get all clubs. It's 1,287. How many ways are that I get all hearts? And spades? And diamonds. Right. Like this is a problem that's just like the last one. It's just that I have to multiply it by 4 because there's 4 different suits of those 1,287 cards that come to play. So when we're thinking about this one, we have the number of ways of getting more than 1 suit. and this is the number of ways of getting any hand, I'm just going to put any, minus the number of ways of getting all the same suit. So this was the 2,598,960 minus 4 times 1287. And write yourself a note. Why did we do 4 times 1287? Well, because there's, hang on, because there's 4 suits. So there's 4 1287s that could come out from doing that. So if I take 4 times 1287, multiply, and then subtract from 2,598,960, what do I get? It's still a lot. Still well over 2 million.
2,593,812.
Right. Now, could I have been asked this question without question number 1? I could, right? But I'd have to just think through this description, right, that I wrote down here. Well, how do I get all hearts? And I calculate it, and then I recognize, well, that's the same question as how do I get all spades and all diamonds and all I miss clubs. And so I would just multiply by 4. So I could take this question at face value and still have created the same process that I did on number 1. All right, let's do another one. Always asking ourselves, what can I not have? 3, at least 1 face card. What can I not have? No face cards. Yeah, so I want at least 1, so I can't have none. So this is the complement of no face cards. So I need to think about what cards are not face cards. So let's just list them real quick. What cards are not face cards? Okay, so 2 through 10, right? And ace. These are the not face cards. Does that make sense? Okay. How many of them are there? How many from 2? How many numbers are there from 2 to 10? Let me start there. There are 9 plus my ace makes 10. But there's 10 in the hearts, and there's 10 in spades, and there's 10 in clubs, and there's 10 in diamonds. So how many are there? 40. There's 40. There's 40 cards like this. The other thing you could do is you could ask yourself, well, how many face cards there are, which is what Sydney was thinking. How many face cards are there? There's 3 times 4, because I have 3 in each suit. So you could say, oh, there's 12 that are face cards, 52 cards total. So there's 40 cards left as well. So there's more than one way to reason through that, knowing what we have discussed anyway about decks of cards. But any way we do it, if we're thinking through it with all the pieces in place, we're going to get 40 cards. Okay, so there are 40 cards that are not face cards. So I need to figure out how many that is. Well, the number of not face card hands, right? Means I have any one of those 40 cards, and I choose how many? 5. I've got 5 card hands here, right? That's the game I'm playing. If you were doing this problem and we were talking about committees or something like that, it's not always going to be choosing 5, right? So just pay attention to the construct of the question. How many people am I choosing? How many can I choose from? There's one that shows up. I can't remember if it's in your assignment or not, but I'll give you an example of something. So let's say, for instance, you had a class of students much like yourselves, and we had some of your freshmen, most of you probably are, some of your sophomores, some of your juniors, and some of your seniors. We could make those our categories instead of hearts and diamonds and spades and clubs, or face cards and not face cards, right? We could put you in categories like that. There are some questions that will put things in categories that are male versus female. They'll put things in categories by age. Are you over 30 or are you under 30? Right? So there's lots of ways you can categorize information. It just needs to pay attention to the context of the problem. Yes?
Why is it 40 and not 12?
Because there's 12 face cards. That means there's 40 that are not face cards.
Are we trying to find face cards?
We're trying to find a way to have at least one of the face cards in our hand. So an example would be, I could have a hand that has like a king and a 2, 3, 4, 5, 6. how many cards? 2, 3, 4, 2, 3, 4, 5. That was enough. 2, 3, 4, 5, and a king, and that would work. That gets me one face card. But I need to find the ways I can get one face card, or 2 face cards, or 3 face cards, or 4 face cards, or 5 face cards, right? Those are all of my options. I don't want to find the number of ways of getting those 5 options. What I want to find is the number of ways that I can't get what I want. I can't get what I want if I end up with a hand that's all cards that are not face cards.
Okay.
So that's the one I'm calculating right now. All right, so this becomes the problem like we did in the last sections, right? What goes on top? 40. What goes on bottom?
30.
5 and 35, yep. And we will write this out. Space there, I don't. Let's put it underneath. 40, 39, 38, 37, 36, and 35 factorial over the 35 factorial. And the, oh, I should write the 35 out. Let me do that. 35, oh no, it's the 5 one right out. 35 factorial. There we go. 5, 4, 3, 2, 1. And we'll cancel our 35s. What else do you want to cancel? So what did you say? 5, 4, and 2 make 40. Sure. 5 and 4 is 20 times 2 is 40, and cancel out our 40. Now what? 3 and the 36, or you could do 3 and 39 if you wish, right? So 3 and 36 gives me 12. So I have 39, 38, 37, and 12. $658,008. But that's not the answer to my question. That's the number of ways I get what I don't want, right? The first step is always figuring out what I get that I don't want. So how do I figure out what I get what I do want? Well, I subtract. So this is the number of ways of what I, and I'll abbreviate it this time, what I want to have happen, minus the number, or sorry, equals the number of ways that anything can happen, minus the number of ways that I get what I don't want. And the don't want I already calculated. So my 2,598,960 minus 658,008. How many hands do I have that are what I'm actually looking for? Does that make sense? All right, one more of this type. At least one diamond. What can I not have? No diamonds. So that phrase, at least one, often turns into no. Depending on how you're phrasing it, you could turn it into all of something else, right? So I can either say, at least one diamond means I want not no diamonds. It's a good double negative for you, not no diamonds. Or you can say all cards that aren't diamonds. So you can change it into alls or no's. It just depends on what follows after that. So this one is the complement of having no diamonds. Okay, so how do I get no diamonds? Well, how many cards are diamonds? 13. So how many cards are not diamonds? 39. So how do we get 39? Just in case somebody's not quite sure at this point.
52 minus 13.
All right, so 52 cards total, 13 are diamonds. We subtract, we get 13. So the number of ways of getting no diamonds is the part I'm on right now. So you said 39, which is correct. And I need to choose 5, because I'm still working with 5-card hands. Could we do this entire problem and do a 4-card hand, playing a 4-card game of some sort? Well, of course we could. And I'm pretty sure there's an example of the one that shows up inside of the homework or quiz or something like that, where they change the number of cards. Lena's nodding her head, so I'm guessing that's a yes.
I tried to do 5 cards.
Yep.
Did you?
I didn't read it.
It was 8 cards on mine.
It was an 8-card hand on yours. What was it on yours, Elena?
Six.
A 6-card hand. Okay, so there's nothing special about the 5-card hand. We're doing the 5-card hand in class, and I'm trying to keep that part of my example the same so that you see the other parts that are changing as we go instead, because that's the more important piece that's going on. But pay attention to the number of cards in your hand for sure. All right, so we have 39 factorial on top. What's on bottom? 5 and 34. All right, so 39, 38, 37, 36, 35, and then 34 factorial over 5, 4, 3, 2, 1, and 34 factorial. Okay. What do we cancel? Let's start with the easy one, the 5. What will the 5 cancel with? Because there's only one choice. The 35, yeah. So let's cancel our 5 and our 35. Now what?
4 and 3 into 36.
Yeah, so 4 and 3 make 12. We could even do 4, 3, and 2, but we'll just do the 4 and the 3 since we saw that one first. So 4 and 3 make 12, and then the 30, oh, we can't do it that way anyway. Take back what I just said.
Why can't we?
12. 36 divided by 12 is going to be 3. I was trying to cancel too many things in my mind. Yeah, we have 3 left. Okay, what else?
2 into 38.
Okay, the 2 into 38. 2 goes into the 38. 38 divided by 2 is 19. Good. All right, 39, 19, 37, 3, and 7.
575,757.
That's a fantastic number. Look at that, 5s and 7s just alternating. What is the likelihood of that happening? Not high. Okay,
So we can calculate it.
we could calculate it. That's exactly right. All right, so we have our 575,757, and what we want is not that, right? So this is a number of ways we get what we want. Remember, that's the goal, which is going to equal the number of ways of getting anything minus the number of ways that we just calculated of getting what we don't want. So the structure is always the same. Figure out how you get what you don't want and subtract. So in ours, I have 2,598,960 minus 575,757. What does that give me?
2,023,203.
Which isn't quite as nice as the last one, but it's lots of 2s and 3s. So I'll take it. And zeros, 2s, and 3s. Okay, so a little over 2 million hands. Okay, so these are the ones that are harder to calculate. Are you ready to look at the ones that are easy to calculate? You're going to really like them. Okay? All right, take a look. These are the problems that involve the word or. So it said not and or, right, in the direction or in the title of the section. The not ones are the ones we've already done. The or ones is the one we're about to do. This is the additive principle of counting. And we've actually seen this before too, back when we did sets. So it's not that it's hinging upon it, it's just another application of the same thing. So if we have 2 sets, A and B, then the number of ways that I get the union is the number of items in A plus the number of items in B minus the number of items in the intersection. If A and B are disjoint, which means their intersection is empty, or intersection number is 0, then the number of items in A union B is the number of items in A plus the number of items in B. And after you write it down, I'm going to show you the picture that went along with this to remind you where we saw it. Okay, so if I want the number of items in the union, what it means is that I want everything combined from the inside of the two circles, right? But if I count the number of items in A, I get all of this space right here. And if I count the items in B, I get all of this space right here. And what happens when I do that? I double counted the overlapping part in the middle, the football shape, okay? So what do I have to do? Well, I have to remove whatever was in the football shape to account for the double counting. Do y'all remember doing this? Okay. This is just the same thing. We're just doing it for counting techniques instead of for sets that have these sort of number descriptions that we saw before. It's the same thing though. Okay. All right, so here's the nice thing about these problems that you want to take a look at. On these problems, there's two keys that you're in this type of problem. The first key is that you are drawing a single card. You're selecting a single person. You're pulling out a single raffle ticket. You're not making a committee of people. You're choosing a single person to do something. It's all about picking one thing. All the last problems we were doing, we were picking 5 things. Well, we were doing 5, but you could have been doing 3 or 8 or 6 or something, right? On these problems, you're picking one thing. All good with that? What that means is there's no combinations, there's no permutations, you're just counting the objects. You're counting the number of females, you're counting the number of freshmen, you're counting the number of aces. It's just counting. Okay, simple counting because it's one object you're picking. The other key that tells you this is the word or. It's showing up. That doesn't mean the or couldn't show up in other scenarios, but it's just another red flag to remind yourself this is the scenario I'm in. Those are the or questions. I'm in 10.5 and it says or. Okay? So these two things put together are to help you to remember when you're applying this principle. So this one wants to know number of ways I get a diamond or an ace. Okay? So I'm going to write out the descriptions as we go. This is wanting to know the number of ways I get a diamond. I'll put D. And then or means union. Okay, so anytime I see the word or, I'm talking about a union. Or an ace. A diamond or an ace. So what do? Well, I count the number of diamonds. And I count the number of aces. And I subtract off, if there are any ace of diamonds. I'll put it the way they have it, ace and diamonds, like this. I don't know why I wrote out ace. It's A and D, based on what I did before. We've been counting these all day. How many diamonds are there? 13. How many aces are there? 4. Now, we haven't counted this next one yet, but how many aces are diamonds, or diamonds are aces? 1. There is one card that is an ace of diamonds. So I need to remove it because I counted it when I counted the 13 and I counted it when I counted the 4. I've counted that card twice. So we add 13 plus 4 minus 1. What do we get? 16. Okay, so comparatively, is this a lot easier than the last problems? Mm-hmm. Yeah, it is. And the real reason why is because I'm only picking one card. All right, that's really the reason why. All right. A number card. So I'm going to put that as not a hashtag, that is a number symbol. All y'all millennial people and younger, whatever you are. I don't know what they call it. What do they call you guys now?
We're Gen V.
Gen what?
We're Gen V.
Z?
Yeah.
Okay, we'll go with
Going
that.
after that alpha.
It's a sharp.
It's a sharp?
Yeah, if
You're in music, aren't you? It's a sharp. It's a what?
An octothorpe.
And
Is that what this is called? An octothorpe? Okay. I look at it and I think pound. That's what they used to be on the phone, and they called it a pound symbol, just so you know, but it's the number symbol we're going to call number. All right, aside from that. Red, a number card or a red. All right, so we want it numbers and reds. So we're going to count the number of numbered cards plus the number of red cards. And I need to subtract off the number that are both number cards and, right, the intersection symbol means and, red. Okay, so generally the first 2 calculations that you're counting are things that you can just do really quick. The last one you might have to think through how many of something really works. How many number cards are there? This one we've already done today once. What are the number cards? They go from 2 to 10. So there's 9 in each suit, and then there's 9 times 4, because there's 4 suits, how many cards? 36. There are 36 number cards. Okay, and again, we did that because we have 2 through 10, which is 9 cards times 4 suits. Okay, 36 number cards. This is the next one you know. Number of red cards, 26. There we go. Now we have to figure out how many number of cards are red. Well, we counted the number of cards to be 36, and half of them are red. So that's 18, right? There are 18 that are number cards that are red. So 36 plus 26 minus 18. 44. Okay, all good?
Yeah, that's right there.
Is it good?
Yep.
Okay, a couple more. Black card or a diamond. So the number of ways that I get black, union, diamond. Feel free to write words out in full if you prefer. The number of ways I get black, plus the number of ways that I get diamonds, minus the number of ways that I get a black and a diamond. How many black cards are there? 26, right? That's the same as the red card question we had before. How many diamonds are there? 13. How many black diamonds are there? 0 unless you're skiing. A black diamond is a slope on a ski slope. It is. Yeah, there is 0. This is actually an example, because this is 0 right here, noticing this, of disjoint sets. That was mentioned over in our description. I'll flip back over here just so you can see it. It tells you down here that if you have sets that are disjoint, which these do happen to be so, it ends up being that it's just the number of items in each set added together, because there's no overlap. It comes about by, by the nature of the question. You don't have to decide that at the beginning of it. Once we got 0 at the end, that's fine. It works itself out. So what do you get when you take 26 and 13? 39. And you can also notice that the only thing that I excluded from this were the hearts, right? The hearts are the only thing that are not blacks or diamonds, and there's 13 of them, so that's why there's 39, because it's 52 minus 13. Another sort of application of the not scenario that we had seen before, but with one single card drawn. Last one, black cards or clubs. So the number of blacks, union, clubs. So I have the number of black cards plus the number of clubs minus the number that are both black and clubs. How many black cards are there? How many clubs are there? How many black clubs are there? 13, because that's what clubs are. So in this scenario, if we were drawing this from a Venn diagram perspective, we would actually have like a circle for clubs inside of my circle for black cards, right? So I don't actually increase the number of black cards by incorporating the clubs. They were already there to begin with. But again, I don't have to make that decision at the outset of the problem. It comes about naturally when I calculate it. So I end up getting just the same 26 cards.